Okay, this is General Relativity Part 2. If you watched the previous lecture on General Relativity, I suggest you go do that now. We talked about space-time, the foundations of General Relativity. I'll cover that in another video. For now, we're going to talk about what General Relativity implies for the universe as a whole. That starts off with what an observation revealed. Telescopes around the world saw that the matter that we see from galaxies, from stars, isn't all the matter in the universe. They found out the mass or weight of galaxies and figured out that, well, the matter that we see in it can't be all the matter that there is. There has to be other matter. And another thing, Hubble, an astronomer, discovered that the universe itself was expanding, and he used this with one method called redshifting and blue shifting. It's similar to the Doppler effect. If you've stood on a street and watched a car or an ambulance or a police car go by you, you'll know that as the police car goes closer and closer to you, the sound of its siren gets louder and louder and louder, but then as it moves away from you, it gets quieter and quieter and quieter. This can be interpreted in the red shifting and blue shifting effect. When an object, let's just call this object A, is moving towards you, then light gets bunched up as it's traveling from object A to you. That means it's going towards the blue spectrum. The spectrum of light goes from red to blue. However, let's just swap this around. When it moves in the opposite direction, when it's moving away from you, light gets stretched out as it's trying to reach you, so it gets shifted to the red of the spectrum. Now, what Hubble thought is that he'd expected to see blue shifting for objects moving towards us and red shifting for objects moving away from us. But what he saw is that our universe is just constantly red shifting. Every object that there is, not the universe is red shifting, sorry, but every object in the universe that he saw was red shifting, that it was moving away from us. So what this means is that the universe is expanding. How does this work? Well, it works in tandem with dark matter and dark energy. All the matter in the universe that we see, our matter, the matter that we can observe, makes up for less than 5% of the entire universe. Just think about that. Everything that you see, from whales to dolphins to galaxies to stars, 5% of the entire universe. Dark matter, the stuff that we can't see, but makes up most of what galaxies and solar systems and what everything that we see, but we know that there has to be more mass to, makes up around 30% of the entirety of the universe. And dark energy, the main force of our universe, makes up more than 60% of our universe. This is the dominating force of the universe. In fact, when Hubble found this out, that everything was moving away, it meant one thing, that the universe must have had a start point. And this was the first start of the Big Bang Theory. That, not the show by the way, the actual theory, that the universe used to be concentrated in what we call a singularity. It's the same thing inside black holes, at the point where our laws of physics begins to break down. The singularity is a point of infinite density and temperature. And that means, due to quantum fluctuations, sometimes the singularity can expand outwards. And I just want you to imagine a spring. When you push a spring down and you let go, it jumps up really fast. Now, double, triple, quadruple, or multiply that speed by any enormous number. It's still slower than this. When the quantum fluctuation occurred, the singularity went from the size of a football to the size of the Earth in under a second, in a tiny fraction of a second. It went enormously huge, and it went into the size of the observable universe, 90 billion light years, still under a second. This singularity became enormous and formed the universe today, and it's still expanding. Here's the thing. Dark energy caused the universe to expand. We don't know exactly what dark energy was, but the main leading theory is that it's just space-time, what we talked about in the last lecture. However, space-time is the emptiness of space. It's nothingness, but it isn't exactly nothing. Space-time is nothing, but it's something as well. What space-time does, actually, it expands, it creates more of itself. Nothing creates more of nothing. So that means that space itself is expanding. And you'll notice when I talked about observable universe, I gave a specific number, 90 billion light years long. That's the diameter of the observable universe. Why can't we see any more of this? Why can't we see beyond the observable universe? Well, that's because that point, those points outside of the observable universe, are all moving away from us faster than the speed of light. Now you may say that's impossible. You just said in the last lecture, and even in this one, that nothing can move faster than the speed of light. Well, exactly. Nothing can move faster than the speed of light. Space is, for all intents and purposes, nothing. Nothing, or dark energy in this case, creates more space and thus expands faster than light at these points. The light simply hasn't reached us yet, and probably never will, in fact. So this is cosmic inflation, and it leads to several other theories of the death of the universe that I'll talk about in another lecture, separate from general relativity. So that was what general relativity implies, and in the next lecture I'll be talking about how wormholes and other objects can still shape space-time. Thank you.